Hello, everyone. My name is Gil. I'm the CEO of 3DOptix, and welcome to another live session of an education session about the 3DOptix software. Today, I'm going to cover a basic imaging system. I'll show you how I build the imaging system, and then I'm going to show you how you combine two beams with a dichroic element. And finally, I'm going to show some interesting example from some latest use cases that I'm sure you'll appreciate, and you'll have good example. And they will be on our warehouse, so you can download them and try them out. Okay. So without further ado, I'll start by sharing my screen. Okay. So what we have here, just for people who don't know 3DOptix. So 3DOptix is an online optical design software. We have here the main screen. We call it the 3D layout view. On the left side, you can see some favorites. So this is the detector and a user-defined source and a shortcut to the product catalog and an outliner. Typically, I like to work where I have the entire outliner like this. And there is another option to add stuff by right-clicking, by locating your mouse in the 3D layout view, right-click, and then you can add stuff from this menu. On the top bar, there is some tools. And on the right side, you will see an emerging toolbar. This is the setting of each and every selected element. You'll see different icons if I select a source or if I select an optical element or a detector. So different icons, and I will see that in a second. Okay, so I'm going now to build a very basic imaging system, and I would illustrate how easy to work with our alignment tools, and it would reflect some tools here and an easy way to work with the software. So I would start with a right-click, and then I would add a light source. So this is the light source, and you can see immediately it shows up here. And I would zoom in with the mouse. By the way, all the controllers, you can see them from here. This is the mouse icon. You press this, and you can see all the controllers. So I have the first light source, and then I would need to locate the source. Just a second. I would need to locate it. So we have a robust coordinate system. So when I select it, it is colored in blue. I would press the move rotate icon, and then you would see a dotted line where this source is being referenced to. Typically, it's the global coordinate system that resides in the center of the 3D layout view. So each and every item that I drop to the canvas is dropping at the height 100. This is the default, and it is a default because we do have optomechanics with mounts, and we wanted to allow everything to be at the same height. So I would change the location, and I would put the source right above the global coordinate system. So you can see it is here at right above the global coordinate system. And then I would go and press the icon of the source, and I would want to change one thing. This is just the radius of the source. And I would change it from 1 millimeter to 10, so it will be more visible for this tutorial. So if I have the source, and what I'll do right now, I would press the propagate simulation. This is a simulation for visualization only. And you can set the numbers of rays that you want to show in the visualization view. And I'll show you that in a second once it will be completed. So if I press the source, again, go to the source icon, you can see immediately this is the 3D layout view numbers of rays. So here, this is the default 30. This is for the analysis. So we can do the number of the analysis we show in the analysis portal. It will be either for total or for per wavelength. So we have 30 rays, and now I want to add a lens. So what we are going to do right now, we are going to build an imaging system. and we are going to do it to change the width of the rays by third. So I would pick up a 150 millimeter plano-convex lens, and then we'll find where the focus is. And then I will add another 50 millimeter lens that eventually would give us a beam that would be cut in third. So I'm going to use an off-the-shelf component. So I'm right-clicking, open the Open Product Catalog, and currently we have more than 42,000 optical elements in our optics catalog. These are optical elements from about 20 different leading vendors, from Thorlabs, Edmond, Newport, and some others, and it's very easy to filter them. Here you can see the number 42,029 elements. And let's start by filtering. So I will do prism. I would do lens, and then I would open the subtype. I would select a spherical lens, and then I would take, let's take a material. I'll do NBK7, NBK7. So now I have filter NBK7, and then I would select the EFL. We wanted to do, instead of entering the EFL, let's change the diameter and select 1 inch, 25.4 millimeters. So this is millimeters, so we'll do 25 till 26. And now I have a list of lenses, and let's pick up the first 150 millimeter. This is a plano-convex uncoded. Here is the arrow that I can open and see more metadata about that specific element. And I can even go directly to the vendor's website and see more data, and I can even purchase from that specific vendor. So I'm going to select this. The way that I do it, I select here and mark it here in the radio button, and then you can see this button becomes blue, and I can add it. By the way, I can add multiple lenses at the same time. So you can see it would add 3 items, but I will do just one. And I can also mark it in star, and then at the top I have favorites, so it will appear on my favorites. I don't want to do it, but I would just want to add it to the canvas. So immediately we see here that this element is in the canvas. Now there are a couple of ways to put this lens into the beam. The first one is by selecting the lens and then right-click, and then these options are relevant to the selected item. And you can see here there's a snap to chief ray. I select it, and then I see a dotted line, ask me which chief ray you would like us to snap. I select this, and immediately it would show up in the center of this chief ray. Another option would work with the referencing and the coordinate system. So I would go to the icon above, the turn off light, so it will be more easy. Okay, turn it off. And then I would take the lens, I would select the move rotate, and then at the bottom you can see pick a different reference system. Currently it is referencing to the global coordinate system. In this case, I would like to reference this to the source. So I would change reference. This is the instruction. And you can see that all the coordinate systems that exist in the canvas would show. And then all I need is just to select one of them. And then you see that the dotted line changed. Now here I have another button. This is reset. It would reset all the parameters in the move rotate window. And then on the Z axis, I would put 100 millimeters. And then I would get it straight on the same axis. And then they would be referenced and like grouped. So if I move the source, the lens would move together. So let's do it back. Now they're on the same spot. Now I would propagate simulation. Again, this is not the full analysis capabilities, which I will show you in a second. Now what you do, you just do it for visualization purposes. And now you see where the focus is. So my next task would be to place a detector at the spot. So again, putting the mouse here, or again, I can change the view here, drag a detector from here, or right-click and add a detector from here. So I have now here 2 detectors. As I mentioned, I like to work like this. Now, what we have here in the outliner, I can extend the view here. So each and every element that I have here, for example, I will take the lens. So the lens here, this is the name of the lens. I can select it either from here or from here. So it doesn't matter where I can select the element. So if I can select it from here or from here. So again, let's take the lens, and you can see that it has a few coordinate system. There is the selected coordinate system. This is the LCS, the local coordinate system, but the lens is composed out of a back surface that has its own coordinate system, a front surface that has its own coordinate system, and has an outside frame. And I can switch between any of those coordinate system or even add a coordinate system and make just one the local coordinate system. So currently you can see that the local coordinate system, if I select it, is the one that is associated to the front surface. Okay, very nice. So I have it here. And now let's just place the detector in the proper location. So I will select the detector and right click. And in this case, there is an additional feature that was added to this toolbar just for detector. It is placing the detector at the spot. This is what we call quick focus. And this feature is available for our professional users. So you can do it by minimal spot radius. This is the case here. And then the same dotted line that is asking me to which ray I want to go. So I would select this path, and immediately you would see that it placed the detector on the right location, which is in the focus. The next thing that I would like to do is add this detector to the input of the system. So I would select it, right click, and do snap to chief ray, and I will place it here. Okay. Now, a good practice, you will see that the rays, the size that hits the detector here is very small if you compare them to the physical size of the detector. So I would need to change and make the detector much smaller, so we would get a good amount of data. A good amount of data is good amount of hits on a certain area. So I would select this. Now the icon on the right side would be of a camera. I would select it. And here you would see a few options. First, it's the physical size. Before I change the physical size and make it small, I would change the opacity because it will be small. I want to see where it is. And then there is another thing. You can see there is the letter F, which represent the front face of the detector. And there is on the other side, the letter B for back. Now, it's very important because in 3DOptix, the detector front faces are the only one who are detecting the rays. So if you accidentally, and there is a chance you'll do it, you'll put the back surface in front of the rays, you wouldn't get any rays. So you need to rotate it in 180 degrees. So now let's select it, again, the camera, and let's make it small. Let's do one by one, and then zoom in. And you can still see that it is still too big. So I would do 0.0, and I think that is good enough in terms of ratio of hits to the size of the detector. Okay, so now what I would like to do, I would like to change the name so we would know. So this detector, changing the name, I would do it from the letter I. So I would press I would delete this, call it focus detector. And then you can see here, I have focus detector. The reason that I have here a lot of elements is I have another setup here, just in case I prepared. So you have another element. So everything that is on the canvas would appear here. And you can have, by selecting this, the same right-clicking here on the outliner, the same option as you click here. And this, let's change the name, and we will call it input detector. Okay. So what I will do right now, I would open the analysis portal. This is the icon for the analysis portal. And there are some detectors here which we do not want to use, so I'll just mark them off. And we have here two detectors. You can see the focus detector and the input detector. So I'll select the first one. So what you can see here, so these are the different kind of analysis. The different analysis when I put the detector would be the free analysis. This is the spot incoherence irradiance. This is a very limited analysis. It is limited in the numbers of rays. It can go up to 200 rays and up to 100 by 100 pixels. If you're a premium user, or if you are using our software during the 14 days free trial, you can use the full-fledged feature, which are all these analyses. So we will take this first spot incoherent analysis, which is the analysis for our premium users. And immediately you would see that the numbers of rays would jump to 1 million. You can go lower, but this is the minimum. And then on the number of pixels, you can change it to any numbers. A good number is 300 by 300. I wouldn't go more than that. But if for some reason, for example, imaging, you need to go for a higher resolution, so I would go to 500 by 500 or 1,000 by 1,000. By the way, for the same detector, I can add another analysis, and for different analysis for the same detector, not for this case. So this one I have already. So now I'll do the same thing for the focus analysis, the focus detector. I would add the detector. By the way, you can see here two light sources. This is light source LS3. So you can see it here, LS3. LS1 is another source that appears here. You can see it here, and it's not relevant for this. And I would even turn it off from here, from the propagate simulation using the arrow, so it's turned off. So I will change this to 300 by 300. And this is the button that runs the full analysis, as opposed to this propagation simulation that runs just the simulation for visualization purposes. Okay. So now I would give the simulation a few seconds to complete. By the way, you can write all kinds of questions while I'm doing the presentation, and I will try to answer them when I finish. So now you can see here some notification that 2 out of 2 analyses have been completed. So we can see the results. So I'll take the focus detector, I click it once and it will pop up. I'll go to the input detector, I click it and it will pop up. And then I can minimize, and you can see an icon here appears, and I can minimize the result. So let's put here these 2 analysis results. So this is the input detector. Keep in mind that this is something that I wanted just to show you. Here, you can see these are our old analysis detectors. Those are deprecated. And the reason is we developed these new detectors. Those are more accurate. And they also have the ability for polarization data. If polarization exists, in this case, we didn't define the source to be polarized. So there isn't any polarization data, but you can see here polarization components X, Y, and Z if it exists. So what do we have here? So all of our analysis tools are the same. So here you can have the type. So this is, for example, false color. You can do grayscale. You can do spectral view. And you can also do cross-section. So each and every pixel you press it, you have cross-section. And then here is the wavelength test. Since we use the source, this is 550. I didn't show you this, but let's press the source and then go all the way down to the wavelength information. You can see that the default is 550. I can edit this. And I can change it. So this is 550. I can add another wavelength if I want, or I can even change the spectrum type to top hat, Gaussian, black body. But let's leave this as 550. Let's open up the analysis again. So since I'm using 550, so I see 550, and there are also all kinds of measurement tools that you can apply on this screen. So what we have here, there is another thing which is important. You can find here this bar. Currently, it is show that this is linear view. If you want to change to logarithmic view, so you can change that, and you can download the data if you want a picture, or if you want the Excel spreadsheet with the data itself and to manipulate it out of 3DOptix. So this is what we have here. Let's complete the imaging system. So right now, I showed you how to add a lens using the catalog. And now I would like to show you how to do a user-defined object. So if you remember, I started that we wanted to build an imaging system, a very simple one that would take the width here of the beam, and you reduce it by 1/3. So I put a 100 millimeter EFL lens, a plano convex, and then I would like to generate another 150 millimeter plano convex lens. And in order to do that, we have here a lens calculator tool. I would open that, and here it helps me to calculate what I need to do in order to generate. By the way, I can go and find the right 50 millimeter lens, and it would be good as well. But if any one of you wants to generate an optical element, specifically a lens, but you can generate a prism, a filter, whatever you want, you can do it with the wizards that I'll show you in a second. So we'll start with the lens calculator. We'll do plano convex. I'm looking for R1. The width, I'll do 3. And then the EFL will do 50. And then we can see the R1 is 25.96. I'll just switch this to EFL, so I'll be able to copy this. And by the way, at the bottom, the default is NBK7. This is the material, same material that I use, and we'll use the NBK7. And the wavelength is 550. So now I'm opening the add user defined object. This is a wizard for a premium user that can add any object. You can see any type from mirror, prism. You can use an aperture. You can use a mask. We have defaults that you can use, our own defaults here, those one, or you can upload any custom element. In this case, we want to generate a lens, specifically a plano convex lens. And then we'll take the geometrical properties. We want a 25 millimeter, thickness 3, and R1 will just paste what we have got from the lens calculator. And the material, will change it to NBK7. So now we have lambda is 550, everything is in place, and we'd save it. What happens right now, so I'm saving this element, and now I would go to the lens icon, and you would see a small icon of a character. What does that mean? It means that when you open the product catalog, here on the left side, I showed you the public catalog of the optics that we have. We do have optomechanics as well. I'll show you in the next example. And we have light sources. But things that you generate and upload by yourself would reside in the private section. So here, this is the private section of what we have done. So I can access it later on. So now I have the lens. So now I would select it because I go to the optical settings, and I have another calculator here. So I just want to make sure that I'm at 550, and I want to see what is the FFL. So I see that the FFL is minus 50, and then I want to make sure that the width is 3. So I have everything is in place. So what I will do, I would need to reference it properly. You can see that this is a very, just a second. I think it created a, yes, I have here, just created another one in advance, this one. I want to show you this. So this one I created right before this session. So let's open this again. Again, this is private. The thickness is 5. Yeah. So the thickness is 5. And the FFL is 49. And I would copy that. You see, I will change again. So it's 49.995. Okay. So now I would get the proper result, even though in this case I would get the good as well. So I would take this, I would turn off the light for a second, because what I would like to do for FFL, this figure that I copied, FFL, I would like to reference it from the focus. So the focus is here. So I would go and select the lens. Now I would change the reference, and then I would select here. And you can see that now it is reference. I would reset. You can see that now, since the coordinate system are opposite, so I would do 180. And then I would, on the z-axis, paste the number that I got. So now I'm ready to run the simulation. So let's do visualization first. So I'll wait a couple of more seconds. I see that it looks okay. So now what I would like to do, I'll add another detector. And then I would reference it and put it on the axis. Let's, again, select it, reference it. I would reset it. Since I selected one of the opposite coordinate system, you can see that it is now, I see the front here, so this is okay. And then I would move it 500 millimeters away. So now, if I would go and change the name and call it far field, and add here, I would follow the same method that I was doing on the other detector and run analysis, just to show you that eventually the width of the lens would be 1/3, and we would apply the measurement tool that I have showed you earlier. So I'll give it a few more seconds. So you can see your notification about the analysis that have been completed. Okay. Good. So I'll pop this up. So this would be the output, and this is going to be the input. So let's just play with the measurement tool. And the measurement tool, I'll take fit to circle. And the instruction how to work on each and every measurement tool is by pressing I. So this is click 3 times with approximately 120 degrees apart. So I'll do 1, 2, 3. I would see R is 10.1 millimeter. And then I would do the same thing here. And then I would get radius is equal to around 3. So I got exactly what I wanted. So this is the first example. I'll now go to the next example. So the next example is a little bit different. So what I have here, so I have here a source, and I would like to combine two different sources with two different wavelengths with a dichroid. So I have here a source. So this is a 700 nanometer. So let's just propagate simulation so you can see that we're talking about a red color. And then I have another one here, which is a little bit bigger. This one is 1 millimeter radius, and this is 3 millimeter, and this is 430. So you can see 430. And my purpose in this session would show you how to combine these two rays and how sensitive this system is. And I would, in this case, I would add optomechanics. So you can see here that I have here this source, and I have two metallic mirrors that I placed earlier because we don't have a lot of time. And now what I would do, I took a bigger mirror, and I would start adding them, aligning this purple ray into the dichroid. So let's take this first, and then do move rotate, and then change the reference to that specific source. reset, and follow the same method, put it 50 millimeters away. Now, I would do another thing. I would put another coordinate system in the same location. So right-click, add a coordinate system, and then I would reference this coordinate system to here, to the back. And then reset. And now I would detach it. So now it's back here. What I will do next is select the mirror and then rotate it in 45 degrees. Try to propagate simulation. You will see that the beam would now be diverged in 45 degrees. I did want another thing, which you have noticed. I've changed the default of the source from 30 to 1, because it's going to be very easy to show it when we have just one ray. So now I'm taking this exactly the same metallic mirror, and I will duplicate it. Okay. And now I would want to locate it right over here. Of course, I would need to rotate it. Okay. Sorry. But first, let's change the reference. So I would select the reference. And if you remember, I've located a coordinate system here, which will make my life very easy. This is the one, which is stand by itself. And now if I reset it, now I would need to move it over here. So it's roughly on 145 minus 145. And then this would be 0. So now I would need to rotate the mirror. So I would rotate it. And now it is, I think, ready. Would still need to play with this a little bit, but that will give you the sense of how sensitive the system is and how you need to work eventually in the lab. Again, in this case, I would start adding I will show you how to add optomechanics as well. So we have another option here when you select the optics, or for example, this optics. So there is a feature of hide inactive surfaces. So you can see that we can eliminate them. And you can do this here as well. So I would hide them. And then you can see the rays here inside. So you can see how it's being diverged, the 700 nanometers. So now I know that I need to move this a little bit. Okay. So I would move this a little bit. So I'll go to the 145. And just try it out. It's very simple to try it out and to see that they will be close enough for us to move to the next phase. So this is not close enough. So let's move it closer. Let's go to 150. And then I think that's going to be good enough for this step. Okay, so it looks pretty much aligned. Okay, so now what I want to do, I want to put 2 detectors. One, so I'll add 2 detectors, okay? And then I would place them to chief ray, and we'll do it on one of them, it doesn't matter. Let's do it. And then I will duplicate and put this one in the far field. And then snap it here. Okay. And I would make it big. So let's do 100 by 100 and change the opacity. Okay. So I have this ready. So now what I wanted to show you, before we are playing with the sensitivity, I want to show you now how we are adding optomechanics. Because for a lab experiment, it doesn't look like that. You need to add optomechanics. So in 3DOptix, there are two options or even more to work with optomechanics. So first, in the view, I would go and add a scene option. I can add a breadboard. So now I have everything on a breadboard. And now I would like to add an optomechanics. So in this case, I know that I would need some kind of degrees of freedom, so I would add a kinematic mount. So I would open the product catalog, and then I would go to optomechanics. So we have integrated about 1,600 different optomechanics mounts and accessories that you have it here. And we even did more. And some of them, the mounts, we even added the post and the post holder. So it will be very easy for you to work with. But if you don't find the mount or the optomechanic element that you're looking for, you can always right-click and import any CAD to 3DOptix, and it would reside on your private directory. So let's bring one of the kinematic mount that would fit here. So I would select optomechanics, and then in the type optic mounts, and then subtype, I would take kinematic optic mount. And then I would scroll all the way down and then a little bit up. And then I would look for the optic size. So size of compatible optics. So since I used 1 inch, so I would do again 25 to 26. And then you can see here that we have KM100. The red icon meaning that it is an assembly. It means that it has a post and a post holder. For some of the mounts, we have, and we can make it more results here. So KM100, and we do have KM100 even without the post and the post holder here. So we have it here, and we have it with the post holder. Again, all of the metadata, the direct link to the website, and I will add this. And by the way, when you bring it with the post and the post holder, you do have the option here to change the height. So it's very easy to do that. And you do have the option to hide the post. So you can hide it if you want just to keep it. But if you want to build a real digital twin that shows how your design would look like, so this is the option. So the first option, when you work with a mount that was defined a mount in 3DOptix, is selected. And then you have an optical icon here. And when you press it, now the optical catalog opens with a filter that fits the size and the shape of that element. So it's circle 1 inch, so you can see less elements. And if you select one, so automatically it would be insert and they would be grouped, so you can work it like this. In this case, I want to show you a different type. So since we already did the alignment, so what I would like to do, I would reference the mount to the mirror, so it will be in the right position where I already did the alignment. So what I will do, so the default of the mounts that are coming in is where their coordinate system is located at the bottom of the mount. It's very easy to work like that when you have a breadboard. But when I want to reference the optical element, I want to reference it in the center here of the mount. So this mount, if you press it, again, let's do it here, extend it. So press the mount, you can see that it has the 3 elements, the mount, the post holder, and the post. And each and every one of them has different kind of coordinate system. So I need to change. So I would hover above it. I'm not selecting it because it is a better view. I right click, and then you can see change local coordinate system. And you can see here, this is the one that I want. So all I need is just press it. So now this is the coordinate system. You can see that when I press this, the z-axis is pointing that direction. Where I press this is this direction. You will see what will happen. So I press the mount, move, rotate, reference, and then I would select this one. This coordinate system is the backside, and it would reside in the right location, but you can see that the z-axis pointing the other direction. So now when I reset, I would get the mount in the other direction. So all I need to do is move, rotate 180, and we are done. And you can repeat that on all the other mounts, and you will get a digital twin. So now I want to show you in this section how sensitive is this system. So we have the big screen, and we have this, and I'm going to play a little bit. I want to show you this with this element. I'm opening this. I have a pin here, so I can leave it open. And now let's play with this. So Y is 45 degrees. Let's do 45.2. So that mirror moved a little bit. Let's do this propagate simulation. So this is a minor movement. And now you will see how sensitive is the system. So you can see that it moves a little bit. And you can play again, even with this mirror, and then you can get it back. Okay, so you can go to the 135 and do 135.2. Again. And this illustrates how sensitive the system is. And you would face this sensitivity when you build it in the lab. And the reason for building a digital twin before going to the lab, or even while you have an experiment already running, is that you can see all the effect here. So you can see how everything here has moved, even more roughly. So it's very, very sensitive, and you can plan ahead which and every mounts you want to buy and you want to apply in order to avoid an excessive degrees of freedom. Here I applied a kinematic mount with 2 knobs. Maybe this is too much. So this is very important. And just to show you to complete, so I would go and change here the source to 30. And I would change here this source 30 as well. And now when I propagate, we'll get the full size of the rays, of the beam. And this illustrates how sensitive it is when you want to combine these two via a dichroid, how the dichroid is actually diverging the beam here, and how you need to work in advance and to do the proper alignment. Okay. So that was my second example of how you combine them. Again, if you do have any more questions, write them down, and I will address them when I'll finish. So what I want to show you right now are additional examples of digital twins. Okay, so what we have here, let's propagate here the simulation. So we have here, will take a few seconds, but we have here, let's rewind back. I want to change something to show you, because here you see the end results, and I wanted okay, I wanted to show you something different. So here I have a microscope example. This is a complete digital twin that will show you very nicely how in a complex design, it's very important to build digital twin to foresee a lot of problems that you will have later on while building this. Okay, so what we have here, so we have a feeding line. This is the red one going into a microson interferometer. You can see the optomechanics here are Edmund's optomechanics as well as Thorlabs, and the optics same, Edmund and Thorlabs. And you can see here from the microsome going here to that focusing lens. And this is a pump that's going in as well. So what we are showing here is adding a delay line via a very simple method way of doing it. So let's go and change the location of this element, and you've seen it earlier. So I'd move this, but since I reference it, so all these three would move. And this is what we call here, this is called a Harriot cell. So the Harriot cell is a way to create a delay line in a very small footprint. So here you will see three bunches. So the ray are going back and forth 3 times and hitting this parabolic mirror 3 times. The Harriot has one of the element has a hole in the middle of the element. You'll see here. So it's a hole. So that was imported, this element from CAD. And this is a parabolic mirror. So we added these elements. You can see now the feeding line goes here and then into the Harriot cell. And from the Harriot cell, it is feeding into the pump of the microscope. Now, in order to get a bigger delay line, so we calculated the distance and we'll change here the distance and we'll do 28. So we moved the second amount. And now I would run an analysis. Keep in mind that I have here a detector. And then I would like to show you how nicely the 3 bunches now become 28 bunches. So we will wait a few more seconds. So you would notice that in 3DOptix, you don't have any requirement for hardware. Everything is done on a remote server. We do the simulation on GPUs, and everything was developed from day one on GPU, so it's very, very fast. You can see that we are running billions of array quite fast. And you don't have any requirement. All you need is an internet connectivity and a browser. So this is a very nice way to apply digital twin and optical simulation. So now it's very nice to see the 28 bunches. So this is the analysis. And now you can see about 28 bunches that we have here. Okay. So that was a digital twin example. Again, I would put that on our in the warehouse. So the warehouse is on our website, and you can go and you can download this example if you want to play with this a little bit more. I'll show you 2 more examples, and then I'll leave some room for Q&A. So this is what we have here. This is diffraction grading. So here we have a broadband source. So you can see here, I go to the wavelength information. It is going from 400 to 700 every 5 nanometer. I'll show the chart. So this is the chart. Every wavelength has a weight of 1. Now, these are, I'll show you what are these. These elements are grading from Newport with 600 grooves per millimeter. So this is this element. Again, for any of our premium users, you can take an off-the-shelf component and edit it, or you can create it from scratch, as I showed you earlier. So you can go and change all the parameters. You can, by the way, go even deeper, go to the surface. So you can go to the front surface and get more information. Now, this coating data, this is the coating data that we got from Newport. So you have that, and you can, by the way, download this. Or you can apply uncoated, or you want to use our defaults. I will not save it, so it will not be changed. And then there are some simulation settings, and if you want to enable scattering, so there are more information here. So let's do cancel. I don't want to save. And then I added here a filter. It's a dichroid. And it has a cutoff at around 560. So this is from Iridian. So it's a long pass. So now let's run here the analysis. So I ran it before, so we have it. No, we don't. Let's see. Okay, so we have it here. So I'll open it up. So you can see, it's very nice to see here all the wavelengths, and you can just select the one that you want, and you will know exactly the X and Y, which will show here where it hits the detector. And yeah, and you can go and change here to spectral view, and you can see the exact colors where they hit it. And you can go even and move this and run it again. And you would get all of the wavelengths would go through all the way to the other side. So let's give it a few more seconds to complete. And you can see here a very nice compressor. My last example, this is a Mach-Zehnder interferometer. I want to show you coherence. So we designed here a Mach-Zehnder with identical two arms. And we have here a beam splitter, 50-50. And let's open this up. And I would get the result. So we developed and we actually created this window that, and we're talking about this detector. And you can see here that it actually, the fringes falls a half a pi. So what I will do here, again, show you the sensitivity of the system. So instead of 45 degrees, we'll put 45.01. Again, this is a very nice experiment to show how sensitive an interferometer looks like. So we did the change of 0.1 degrees, and in a few seconds, you will see how that affects the entire result in the two arms. So the results are coming in. So the first one is in. Second, you can already see the results. Third one is done, and we'll wait for the last one. By the way, you can press stop here. You do not need to wait for the entire simulation to complete. So when you pop that out, so you can see how that was changed dramatically, and you can go again and play with the material. You select the material and change here the width, the thickness, and you can see how that affects the system. So those were my examples and the training that I wanted to show you, targeting labs experiments. And now I would like to leave some 5 minutes for any Q&A if you have. And I see that you already have, so I will try to address them. Can I add a specific laser as a light source? So the answer is yes. So I want to show you a few things here regarding this. So I'll open up, again, I will share my screen with you. So when I add a source, okay, so let's take the source. So the one that we support currently are here, source type. So we plane wave, point source, and Gaussian. We are very soon going to support upload of IS-25. When you open the product catalog, you can also already see a few sources here, but very soon is a couple of weeks, you would be able to see some LED here, about 40 of them, and be able to upload any IES-25 file that you have. Of course, this is for our premium users. The next question, can we add the slit and aperture in optical setup? The answer is yes. So what you can do is go to add user-defined objects, and then you can create an aperture here and define it. And then once you save it, you can find it over here. You can also add a paraxial lens here, and you can define it as well. And the last nice thing that I want to show you in add optical element is our ideal microscope objective. So you can see here, since the objective vendors do not share their internals, so we created a widget that would build ideal objective from paraxial lenses. All you need to play with the parameters here. So you play with the magnification. Let's do 50. So you can see 50. Everything would be imprinted, by the way, over here. And once you save it, so you have here that as well. Hope that answered that question. Michael, it was a very nice presentation. After we build the model, will it be possible to update the model's parameters, say mirror alignment, via script or config file? Okay, so we do have APIs, so Python APIs. So if you go to help APIs, so you can find instruction how to do that. And we also have on our website, if you go to 3DOptix.com, we had a webinar about APIs. So you need to download an SDK, and the SDK would approach the API. So if you go to our website, resources, and then go to video, and under video, there is 3DOptix live session. Like this one will be uploaded to this section as well. And over here, you can find a session about the APIs. Let's see where it is. Maybe it's on the webinars. Here, diffraction, 3D polarization, and APIs. So you can find it here, and you can see a 1-hour session with one of our developers. Also, how we can see, for example, an image in detector, for example, fringe in a Michelson is possible. So I showed Michelson. There is a nice example of imaging, which I'll just show you in a second. This is I'll open up a US Air Force 1951. Okay, so here, this is already, I don't want to show it now, but what we have done here, so we have a filter here that you are familiar with. And we have here a diffusing surface. So it can emit a lot of light from each and every pixel. And this one actually works. Let me see if I have something which is already in place. But since you surprised with this question. Okay, let's see this, which is very similar to what we have here. So I would need to run it, so it will take here like about a minute because these are a lot of rays, but the answer is yes. If you'll send us an email, I can send you this design. Send an email to info@3doptix.com. Again, is any limits for distances to sensors? 1 kilometer? No, there isn't any limit. How can we add a diffuser? I showed you this already. Okay, so let's see if we do have more questions. I would leave. Okay, Philip, do you examples for laser system with Gaussian beam like of 3D scanner system or other lasers application? What do you mean? I'm like for 3D scanners. Well, I don't have right now, but we can show you this. You can again, Philip, send us an email to support@3doptix.com or info@3doptix.com, and you can schedule a demo for if you are intending and you want to see if you want to buy a license, so we can do a demo directly for you, and we can show you exactly what that. But the answer is yes. Any more questions? Okay, so I'd like to thank you very much. We're going to have another session in about 3 to 4 weeks. If you have any requirement, so let us know. If you have any wish list of a session that you would like us to present to this nice audience, again, let us know. So again, thank you very much for attending. It was my pleasure to present this session, and I hope you will use our system. Thank you, and see you in our next session. Philip, I do have a recording for this, and it will be available on our website in about a week.